Hello, everybody. Today I'm going to talk about an article that's called A Multitubular Kidney on Chip to Decipher Pathophysiological Mechanisms in Renal Cystic Disease. Autosomal dominant polycystic kidney disease, ADPKD, is the most common genetic renal disease and the fourth most common cause of end-stage renal failure worldwide, without curative therapies except dialysis or transplantation. ADPKD is characterized by enlarged kidneys in which progressive numerous and bilateral fluid-filled cysts extend from renal tubular epithelial cells. Human cysts could reach up to 3 millimeters in diameter, detach from the parent tubule, and migrate away while continuing expanding. Expanding cysts constrain the function of renal parenchyma and participate to its progressive failure during ADPKD evolution. While many studies focus on the genetic and molecular factors involved in this disease, the prominent influence of geometrical and mechanical factors has not yet been investigated. Recent studies on ADPKD patients and specific mice models suggest that primary cysts are randomly formed along the renal tubule, but the secondary cyst formation tends to be spatially clustered. Expanding cysts or dilating tubules may exert a mechanical influence on adjacent tubules, either by direct cell compression or by flow disturbance due to the locally altered shape of tubules. To decipher the geometrical factors involved in the propagation or deformation between adjacent tubes, the authors propose here to reproduce those physical properties by developing an array of renal tubules in advanced in vitro models called kidney on chips. In this paper, the authors report on a microfabrication approach to recapitulate renal tubes of physiological geometries positioned in parallel with 100 or 200 millimeters spacing in a biocompatible and deformable hydrogel. Using this unique device, we studied tube behavior upon seeding with several epithelial renal cell lines and focused on tube deformation with an ADPKD cellular model. Now we are going to talk about the microfabrication and the device design used in this article. In this figure, we can see the design of the chip that we are going to talk about in this following section. The design of the chip was first drawn with CATIA and mailed on a 50 by 50 by 3 millimeters brass block with a micromiding machine. The parents were then transferred via hot embossing at 100 Celsius degrees, 7 bars of pressure during 10 minutes on a 2 millimeter thick cyclic olefin copolymer, or COC plate. This COC is a thermoplastic displaying an optimal optical index for the tube's visualization under a microscope. On the COC plate, this is what is the COC plate in the figure. This is in gray color, and this in the figure 1.b. On the COC plate, the parents comprise a rectangular reservoir, which is observed here in this section. This is the reservoir. The measures of the reservoir are 1 millimeter wide, 5 millimeters long, and 300 micrometers deep, in which the tubes were molded in collagen 1, 1 millimeter long. This is the collagen tube. This is the mold of the tubes that are going to be filled with collagen later. They have measures of 1 millimeter long, 90 millimeters wide, and 90 micrometers deep group on each side of the reservoir, separated by 100 or 200 micrometers. This is the separation that is going to vary from 100 to 200 micrometers. We are going to see later why this separation changed. In these separations, the wires are going to mold, are going to be positioned into the bond. Two connectors with a semi-cylindrical bottom at the side of the COC plate, this, were placed at both extremities of those rows with a continuous transition. Liquids and cells were injected through those two connectors. In order to obtain an adequate covalent addition of collagen 1, the CO0 reservoir surface was first treated with an oxygen plasma. This surface was first treated with oxygen plasma. And then it was cyanized with 2% of 3-aminopropyl 3-ethoxysilane in phosphate bufferylene, followed by 0.5 of glutaraldehyde in PBS. Each of these incubation steps lasts 30 minutes at room temperature. Between both incubations, the chip was washed 3 times in the ionized water before immersing it in water and incubating it at 4 degrees Celsius overnight. 2 short silicone tubings were bonded in the connectors with epoxy glue. This is not observed in the figure. Then 5 tungsten wires of 80 millimeters diameter. These are the tungsten wires that are going to mold the channels. These were incubated during 30 minutes at room temperature in a 1% bovine serum albumin or BSA solution in PBS. And then they were gathered through the 2 silicone tubings before being positioned in the groups of the COC base. So we have 2 silicone tubes, and inside the tube, there is the tungsten wire. Afterward, the COC plate was covered with a pressure-sensitive PCR tape. This is the PCR tape, and it is going to make that it's going to cause that the wires stay in the place that we desire. The PCR tape is located everywhere everywhere above the tungsten wires, except for the reservoir, which stayed open. Finally, the central reservoir and the connectors were then incubated in degassed and filtered PBS for 1 hour at 37 Celsius degrees to absorb bubbles forming at the group. Afterward, the degassed PBS was removed from the COC plate beforehand put at 4 Celsius degrees during 15 minutes and replaced with 80 microliters of collagen 1 mix. Is this a step? In this figure, we can see the step where collagen is placed, and it's going to replace the tungsten wire. It is gently poured above the open reservoir. The whole setup, once the collagen is polymerized, was incubated at 37 Celsius degrees, 5% CO2, and under humidified atmosphere for 2 hours, before placing a PBS droplet above the collagen 1 mix to keep it wet. This last step is crucial to shape the empty tubes, which will be observed here, where the kidney cells are going to be cultured. This polymerized collagen never stayed dry. This is very important. After collagen 1 polymerization, wires were gently removed through the connectors, which is observed here in this step, in order to get 5 empty cylindrical microchannels here. This is the 5 empty cylindrical microchannels. From this step, the chip remained immersed in PBS or cell culture medium after the seeding. In this paper, the author described the development of a new generation of kidney-on-chip with parallel aligned circular tubes of 80 millimeters diameter and 100 or 200 millimeters spacing in a biocompatible and deformable collagen. This chip was designed to reproduce geometrical, mechanical, and biological characteristics of an array of renal proximal tubules with the aim of study physiopathological mechanisms of ADPKD. They first observed that the tubes were nicely colonized by different renal cells with a long-term survival. Here we can see that the tubes were nicely colonized in both models using PKD1 more and less positive and negative, PKD1 positive and negative cell lines, and using PKD1 negative cell lines. Here we can see the comparison on the deformation of the tubules using PKD1 negative cells and using PKD1 positive negative cells. Here we can see that there is a difference in the maximal deformation, and it is observed when the PKD1 negative cells were used. This comparison was performed using a 200 micrometer separation tube. In the next figure, we are going to see the same comparison, but using 200 micrometers. Sorry, it's not the same comparison. Here we can see the comparison between the 200 micrometers space chips and the 100 micrometers space chips. So we can observe a higher deformation when the 100 micrometers space chips are used. So this separation is the best to be used if we are going to study the deformation of the tubules caused by the ADPKD. Again, according to the scope of this article, they show that contrary to PKD1 positive and negative cells, PKD1 negative and negative cell line is a better ADPKD model. The authors were able to induce using this an important tube deformation. These observations agree with tubular dilation expected for this disease, demonstrating the physiological relevance of this model. Furthermore, this multitube chip design with the spacing between tubes reduced to 100 micrometers allowed for the first time to reveal possible mechanical coupling between tubes, which could play a central role in ADPKD cyst propagation. Altogether, the crosstalk between renal tubes in this multi-tube chip is in good agreement with the cooperative behavior of a snowball effect involved in cyst propagation in ADPKD, and in line with these results, this device may also be of interest to screen for drugs that would inhibit this crosstalk behavior favoring renal cyst propagation. Thanks.